Record. We're starting.
Zoom way better. I can just
What's that?
I like it in Zoom way better than WebEx because they're give you the host, walk away.
Yeah.
Set it for
I just wish this.
you don't like that up there.
It's hideous. I mean, it's taking up like 5% of my screen space.
Let's see if they could go more. Maybe there's like a better view to it.
Hide video panel. That's the other button. Yeah. No, I think that's.
One of the things for you is like if you're just going to be showing this, you can hide it somewhere, but like. When Don gets here, just make him the co-host so that way he gets to the chat.
Yeah, of course.
I can hear perfectly here.
Great.
I know your students are joining online.
Perfect.
If you have seat issues, just let me know. You should have seat issues because they're be online.
Right. Yeah. Cool.
Others.
Hi, Don.
Thank you.
Front row. Or anywhere. It was really.
Katrina.
Perfect.
No, so yeah, so there's bound. You bouncing or I'm bouncing?
No, I'm bouncing.
Okay.
Get out. Big joy. Class.
Team. Under. I hope it's not an issue. Cool.
I need to give you this.
Same meetings yesterday, yeah.
And yeah,
Right.
that should be the plan. Yeah, this bar is so
The bar.
hideous.
Yeah.
Oh, I can move it down.
Yeah, it goes Leave it a little bit.
Leave it up there. Like that. You could do that. Just trying to make sure I can still see.
Before class, go put the attendance. The ones in dark are the ones we're trying to get credit for the class.
Oh, cool. Yeah, you did the same thing I did. Perfect.
Who's gonna pass it around there?
No, that's yours. Stats. He has those.
Yeah, I'm doing this one audibly, verbally. It's so fun. Yeah. And I think we should start. Great. Okay. Welcome everyone for day 2. Hopefully we've got things ironed out, although I think, well, yeah. You should have all received an email last night from me that was talking about a few points, recapping from yesterday, giving you materials for today, and then also talking about the seed issue we had. So I'm going to do roll, which is going to be some fun. So I'm going to go through the list of names for folks. When I get your name, please just raise your hand, say here, I, whichever favorite single word you have. Here we go. Matthew Romero. Great. Shasha Zhang. Thank you. Lily Gong. Thank you. Paula Leon Mamila. No, Paula. So maybe later. Soon, like, okay, right, okay, thanks. Marcelo Francia, thank you. Leonardo Dionisio, thank you. Eileen Nava, thank you. Panteha Hayati, let's see again. Weichia Luo, Weichia, no. Let's see, Ming Wang. Yan Shu. Let's see. Could you tell me your name real quick, sir?
My name?
Yeah.
Daniel.
Danielle Troy here. Perfect. Ma'am? Sorry? Golnish, right. Thank you. Ming, perfect. Thank you. And ma'am, your name? Felicia. Okay. All right, back here. Yan Shu. Didn't get the no. Kirtana Sarathi. Thank you. Carrie Weiss. Thank you. Nick Santa Barbara. Thank you. Jessica Seleska. Thank you. Asli Yildirim. Thank you. Stephanie Luke. Great. Thomas Hodder. Great. Nina Lacheva. Thank you. Ignacio Garcia Mancia. Thank you. Afshin Azadika. Afshin. Nope. Ariel Flora. Great. And Agustina de Gainza. Perfect. Thanks. Great. Thank you, folks. And for the folks who are attending remotely, thank you for understanding, and let's continue. So I successfully sent the blank version of today's worksheet. We're going to work through that, but I also sent the full version. Some folks made a good case to me that due to differences in typing speeds, it just is helpful to have that as a reference in case you do get left behind. So I really encourage you to work through the blank sheet. I'll be typing, and I'm not the fastest typer. I'll use Tab Complete. I'm going to try to speak slowly. So, and it's very good for you to have that sort of tactile experience learning this. So yeah, that's that. We're going to start with picking up where we left off yesterday with looking at graphing and a few more additions to our graphs in terms of like the legend, axis labels, graph title. But before we start that, are there any questions from folks following up on what we covered yesterday? Have you had the night to let things sort of settle in? Okay. So opening the blank day 2 file. I already provided you some of this code so that we can quickly get back to where we left off. So we're just going to tab through. Remember, you always have to set our working directory so we can access the data for today, that iris file. I've got this already set for mine. Go ahead and take a moment real quick to try and change it for yours so that you your working directory points to where that folder is. And remember, if you don't want to type or tab complete it, you can also locate it by clicking on the session button and then scrolling down to the set working directory option. Okay, so once you've done that, then we execute the command to read the CSV file iris.csv and assign it to the variable name iris. Then remember we were making a histogram of this iris data, and we had those 3 different histograms for each of the species of the irises, and then we had those vertical bars to represent the average value of each species group for the sepal width. So we're going to execute those commands again to calculate those averages and assign them to variable names. And then we had to define that extra data frame that collected those 3 average values. Here I'll click on the this means data frame, and we had to define this data frame that had the mean values in one column and then the species names in the other column. So that when we come down to this block of code to make the graph, we start with, we have this ggplot code. The data we're plotting is the iris data set. The x-axis along which we're graphing is sepal width. Fill parameters so that we can color by the different species groups. Those 2 items, the x-axis and fill parameter, both go inside this aesthetics command for the main graph. Then we have this plus sign to add the call for the histogram. We're going to use 20 bins. Position is identity, which means all those histograms start at the same horizontal line. And the alpha parameter is at 0.5 so that they're 50% transparent. And then we have this call for the vertical lines, geom vertical lines. And here we set the data to be the means data frame. And because the vertical lines, right, the vertical lines defined along, they have x-intercepts, so you have to specify the x-intercept for each species group based on the mean values column from that means data frame. And the color of those bars we're using to be set with the species column also from that same data frame. So I'll run all three of these lines by highlighting or command control returning through each one. Oh, I have an error. I forgot to load the library for ggplot. That may or may not have happened to you too when you tried to run these commands. I got carried away. So first I need to type library ggplot. 2. Command return. Now I should be able to run these lines for making the graph. And we did. Graph's in the bottom right. Perfect. Okay. Ooh, a blank section, finally. That's the way it was meant. Now we're going to add a few more details for this graph itself. This is getting into the nitty-gritty of working with some of the plotting aspects. So for example, the legend labels the defaults. So if we're doing histograms, the default is just word count to represent the fact that it's a frequency count. We can change that to be a little more descriptive of what the data is. And also the x-axis just, ggplot just uses the column name for the x-axis by default. So if we want to make that something a little more presentable, we can modify it. So to do this, we copy and paste this plotting command we keep reusing, this whole ggplot plus geom histogram plus geom vline. I'm going to copy and paste that in this next blank section. And then since we're going to change the labels, I'm going to add a plus to the end of the last thing we have for this ggplot block. Hit return and type labs for labels. And we're going to change the title of the X and the Y labels all at once inside of this command. So first we'll start with the title. I'm going to make this be a histogram of sepal widths for 3 flower species. Of course, whichever title you want to type is fine. X-axis I'm going to call sepal width, all in quotes, and then y-axis, so I have y equals for the y label. X equals the X label. For the y-axis, it's just going to be number of measurements. We highlight all of these lines now, command or control return. Then in our plot window in the bottom right, the graph itself has been squished to fit these new labels, and the title, here's our title, and then we have our X and Y axis labels showing up. And things look like they're getting a bit squished. We try and give the graph a little more room. It doesn't always, oh yeah, no, it did re-render. So now we can see here's the whole title formatted and fitting in the graph space. Okay. How about entries in the legend? The legend also comes automatically from the text that's in your data file, the data frame. So the species, right, comes from the column name, and then the species names themselves, excuse me, those come from the actual entries in that column. Those are the different levels for the factor of species. But maybe we want to capitalize these. Maybe we want to change them all together. So for that, procedure is a little similar. We highlight this whole block of code we had from before, copy and paste it. Going to add a plus sign to the end of the labs command, return. Now we're going to add another command in order to change a different aspect of the plot. So there's no good way to explain why this command is named what it is. Just type it. It's called scale fill discrete. We could speculate what each of those parts comes from. Scale has to do with we're modifying the legend or possibly an axis for ticks. Fill has to do with the fact that we're looking at the different color fills for the groups, and discrete because it's a discrete, we only have these 3 different groups as opposed to a continuous axis of values. I'm really just sort of reading into those words though and making best guesses. Point is, I know that's what we need to use to modify this legend, so we're using it. Maybe we can add a comment here at the end of this to saying this function modifies legend. Okay, what goes inside the function? I want to change the name of the legend to be a little more descriptive. So I'll make it species name. To do that, we have this name parameter. So I have name equals species name, comma. And now for the labels, inside of the legend, we use the labels parameter. So I have labels equals. Now, since we have 3 different labels that are going in the legend, we have to define momentarily a vector. So we use the C function, C parentheses, and then we type in quotes the names for the species that we want. And I'm going to use the same name, just capitalizing the first letter. So I have Setosa with a capital S, close quotes, comma, open quotes, Versicolor with a capital V, close quotes, comma, open quotes, Virginica, capital V, close quotes, close parentheses, highlight this whole block again, Command and Control return. Oh, great. Here we go. So for one of these legends, well, okay, what happened? So our legends split. We have 2 legends now. For one of these, we have exactly what we wanted, the species name for the legend name, and then capitalized species names for each of the fills. But now for what happened here, so okay, ggplot knows that we're graphing 2 different things. We have the histograms, and then we also have the vertical lines. And we have legends for each. We have a legend for the fill colors for the histogram, and now one for the line types, also for the vertical lines. And it may be that maybe you have different information be conveyed in these 2 different lines versus bars. And so you would want different legends. For us, these really do mean the same group, so we could try and merge them back together. Or we could use the fact that these are for the means, this upper legend. And if we wanted, we can enter the mean values. So that's what we're going to do. We're going to use this second legend to present the mean values instead of just having redundant 2 legends. So yeah, perfect. All right. So as before, we're still using the same block of code we've had before. So we're going to highlight this whole thing once more, copy, paste it beneath. And again, it's adding the plus sign, and then we're going to just add on another function to modify this next legend. Okay. So this next function has a similar scale underscore blank name. This one is scale color discrete. And the logic that we use to argue the first one for the fill corresponding to the histogram fill, we're going to use the same for this function. Scale color discrete has to do with the fact that we're looking at the colors that have been defined for these vertical lines. So if you go back to where you define the vertical line, remember we have this aesthetics parameter, x-intercept for the mean values, and the color there's for the species types. So it helps give you kind of an idea of, oh, the histogram is where we have the fill information being used, and that fill corresponded to the scale fill discrete, and then the other object we put into the graph were the vertical lines, and we're differentiating the items there with the color parameter, which is connected to how we're using the scale color discrete function to modify the legend. So again, we'll change the name for this legend. We'll make this be sepal width mean, if I can spell. And then for the actual labels, we'll make these be the mean values themselves, the numerical mean values. So again, we use the C function. And then I'm going to grab the column of mean values from that data frame we wrote, that means data frame. So we have means, $sign, I'm going to grab the mean values column. Okay. Highlight again this whole block, Command or Control return. And now we have the same graph as before, but now this legend for those vertical bars says sepal width mean, and then we have printed are the mean values for each of those vertical bars. So in addition to having them visually located in the graph, you can also have numerical values tacked on to know the exact value. Any questions from folks on these last parts, modifying these parameters in the function? Okay. If we want to change the font. I have never changed the font. I'm certain we can do that. Dare I? Sure. Take this as a learning opportunity. We'll Google. When I think of something I want to do and changing the graph, I usually just what's the most descriptive, shortest phrase I can think of and put it in the search bar. Change label font in our ggplot. Right, remember there's ggplots in basic plotting. It's important we write ggplot. Let's just see what comes up. Great, first hit, changing fonts in ggplot2, Stack Overflow. To check, this was from July 2016. That's not too long ago, so that sounds okay. If you find something that's like 10 years old, I would maybe not look at it. This is from Stack Overflow. Stack Overflow is a great website for finding a lot of this information. It works like Reddit. Thought I'd say that in the class, that's funny. Where people rank responses that they like for questions and also ranking questions. So here someone's asking something about how do I change fonts in ggplot? And here, the answer that has the most upvotes and was acknowledged by either person who asked it or someone else, I don't actually know this part. They gave it a green check. It's the accepted answer for that question. It's usually a good idea if that's the one you should look at. But there's oftentimes good information below as well. They wrote an essay on how to change fonts, lots of examples. That's why they got the green check mark. The information's there. It is definitely doable. Look, it looks like theme. You add on another element called theme. Let's just take it, see what happens. So I'm doing plus. I have this function theme, text equals element underscore text, open parentheses. They're changing the size and then they're changing the text style. That works, but let's see if we can have some fun. That happens. Got some warnings. Nothing came out. Okay, so, and that's also not unusual. There's some errors that involved. It may not be as easy just copying that code and pasting it directly into what I'm trying to do. I might have to do a few more things to massage it into place. Or it's just that the Gothic script, they don't like it. Oh, but Comic Sans exists. Perfect. Definitely works. Yeah, so very doable. Has to do with themes. Great question. Any other questions from folks? That's kind of a fun font. Okay, last part, saving the graphs. This is really important. You should, all right, so you can save the graph from RStudio by clicking on export. I really don't advise it unless it doesn't matter that this graph is poorly formatted. Like maybe it's just a meeting with your advisor or your students and you just a quick save of the graph. This is sufficient. You can save it as a PNG, I think, or as a PDF. That's fine. But the problem is this exporting option either saves the graph exactly as you see it in this window, which makes it hard to reproduce if you change the dimensions of the window, or you can try and toggle in here specifically width and height, but you can't specify things like resolution. So instead, we use a function to save this to a file. For all the different file types, there are different functions. I tend to use PNG, so I'll use the PNG function, but there's one for PDF, there's one for SVG, and TIFF and JPEG, I believe, as well. This PNG function basically tells R, okay, we're going to save something to a PNG file. I want you to open up a blank PNG file, and everything that comes next, our plotting code, is going to send the plot information to that file instead of sending it into RStudio. The first thing we do is define the file name. I want to save this to. Since we're already in the working directory that I want this file to go to, I'm not going to type anything but the file name. But you could save this file in another directory. In that case, you just type the whole directory / the file name ending after that. I'll call this first graph.png, close quotes. And the nice thing here, so now we can specify the width. I'm going to save this as 11, height as 8.5, units are in inches, and the resolution is 300 dots per inch. Now, after this function, we copy and paste our block of ggplot code. There's no plus sign needed. Oh, this is getting messy. Almost fit everything. Perfect, okay. So we have here is our PNG function to save the file. Here's our big block of ggplot code. And then the last thing we have to do here is enter the function dev.off, open close parentheses, for device off. We have to tell RStudio we're done plotting everything else that we don't want you to save anything else into this image, so please close the file so that it can now just exist as a file, and then we're gonna go on with whatever else we're doing in RStudio. If you didn't add that, any other plots you might make afterward would also be saved into that image. So let's now run this whole block of code, command or control return. When you do this, nothing new will show up in your RStudio plot window because everything has been sent to the file in your working directory. So to check to see that it worked, one, look that you have no errors. There's no errors, that's great. Navigate to the folder. Here we go. This should be your first graph. Looks like it's in Comic Sans, so yes, that's it. And now you have saved your graph to a file. Okay. Any questions on saving graphs to file? Yes. Oh, sorry, what was that? Export. We just did. So that's what we're doing, is exporting the image. But doing it without using the export button. Maybe that's. Sorry. Did you have your question? 32 warnings. Wait. Yes.
Can you save the file in other types like PDF tip?
Yeah. So for that, we just right. Question was, can we save the files in a different file type? And the answer is yes. We just use a different function. So if we want to save it as a PDF, I type PDF, open close parentheses for the PDF function, and then I can specify, again, file name, width, height, and then some other aspects that are specific to PDF files. TIFF, yeah, with 2 Fs. Also, we can save as a file type SVG for support vector graphics. We can also do JPEG. Yep. Any other file types? EPS should also. Oh no! So sorry. RStudio does not support encapsulated PostScripts unless someone wrote. There's a chance that someone has written their own function to do that, and you could just like copy and paste that function, and it would work. In the export mode, yeah, it might be a parameter in the PDF possibly, because those are similar. I thought maybe not. I don't know. It's common. It should exist. Any why do I not like using the export? Because let's see, if I try to save this as an image, I can specify the width and the height. I'm pretty sure I can't specify the resolution in here. But so if I need to come back and edit the figure again, I have to have written down the width and height that I used when I come in here, so that I can make sure I use the right size. And if I'm going to use the figure maybe for a poster or a presentation, I want the resolution to be high. I don't know how I can easily set that within this option for the export button. Also, which we're going to do a little bit later, maybe you want to make mini graphs and you want to automate the process. We can't really do that with the export button, but we can with these functions. Okay. But yeah, like just for a quick save, it's super convenient to just push that button and have it done. I definitely do that. Oh, yeah. So you mean the yeah. Yeah, this one always comes before the ggplot commands. Do you want, okay, so 3 graphs that we're saving. Different what, sorry? So, do you mean like on one page you want like 3 graphs, like here's a graph, here's a graph, here's a graph? Yeah. Yeah. Different names. Yeah. Wait till the end of today. That's exactly what we're doing. Yeah. We can, I mean, in short, you just give them each a different name. And then each one gets saved with a distinct name. Okay. All right, so for now, to finish off the end of yesterday's recap, we're going to do yesterday's breakout session. So what I want us to do for about the next 15 minutes is open up the Hawks Day 2 CSV file. It's another set of data I've shared with you. It's just for, well, it's different. It's not flowers now. It's for birds of prey, hawks, sorry. And now you'll use the variable tail from histogram data and the label species name for the legend. And then I've given you some suggestions, you know, maybe don't use the whole species names, but change them to be abbreviations. And do a similar kind of calculation. You present the mean values for the tails for each of the species in the legend, as we did with the flowers, as well as the vertical dashed lines demonstrating the values. Try working on this with neighbor, you know, break out into groups, bounce ideas off each other. And then I'm going to circle around and, you know, help folks troubleshoot along as you go. Dawn can help, I think, with folks locally, but you've also got the folks online who might have questions with this. So I think maybe just try and watch for them too. And the quick hint, be careful about going straight to that last big block of code and then just trying to modify everything all at once, because you might, subtle errors can compound in that fashion. So I suggest maybe starting earlier in the tutorial and kind of working through and tweaking the different steps to get to the end. Okay.
So wherever they saved it will be in the current working directory.
Yes, is a question that came up. Yeah. Cool. 15 minutes puts us. Oh, perfect. Let's see if there's a way I can display more at once here. Oh, yeah. Oh, perfect. Whoa, there we go.
Yeah, you can't just do CSV. What are you trying to load it? Which are Are you sure you're in the right working directory? So what do you? Oh, there too.
Let's go to
So type ls.
tools.
So type ls. Did you find it or not? So type ls and left parentheses, right parentheses. Ls, left parentheses. Left parentheses. Right parentheses. So that tells you the files that are in your current working directory, and I don't see the Hawks file. Enter. So type get wd and the parentheses get.
Maybe real quick, exit this and save.
Not type that. No, just what I said. Just get working directory. Just that. So that's where you are. And that's the files that are in there, and I don't see. So if you expect to see Hawks, you should find it on your computer and see where it really is. Workshop day 2. Yeah, looks like it. I see Iris,
So
but I don't see any of these.
yeah, the graphs worked,
Is there another?
but it's
Is this under desktop?
Legend of this right now. So this error.
Day 2. I see Hawks. Day 2. This PC.
You go back down to where this code was executed. It's weird, that was like- Yeah, maybe here. Can you try running this? You can see it not work. Well, that worked. Great. That will work.
Yeah, no, that's weird. There's something trying to figure out the present directory.
Maybe try getting rid of the Steam one just for now. So we can see if there is come in here and type warnings, open for parentheses.
Okay, so it's a different thing. Okay, hold on. Now it's list dot files.
So I wonder if it's
Yes,
just
yeah,
because of the size
yeah,
of
yeah,
that, that it's giving it an error. It's- Everything graph. If you try doing the ones, the PNG,
Now what was the
and
function
then
you
we
wanted to
can
cross?
see if it made the graph.
You wanted to open up the CSV file?
I think that
I don't think
let
it's
us know
view, I
exactly
think it's
might have to
CSV read or something, but it's just striking it.
fit everything in the graph into that space.
What do you tell me? Read.csv. Yeah, do you have a first day? Read CSV and then file equals. In quotes. And then maybe sure, but you should have this exact code in your code already. Figure it out. Like you've already opened this. You've already done this.
No, this one just is real for Iris.
So what are you trying to do? Are you trying to open up this Hawks file?
Yeah.
But you already did. It should be in your code. You already opened CSV files. You already you don't need to manually type this. You already have the code opening up CSV files. Yes.
Yes. No, yesterday we couldn't use that file.
Never mind. Go ahead and type it. Go away. You might have to add. I don't know if it has a header or not.
Oh, yeah.
Yeah. So it's your options are header is true and separated is comma. I think you got it right. So, this is good. Yeah. Okay, that works. That works. For the moment, or you just
I want to make sure it's after that, go back and file or just with the first we have. All right.
It's not your risk.
So,
You have to load the data if you want.
oh, okay, so I can agree.
So you just assign that to a variable.
Okay, yeah, so that has to be, it's supposed to be a column. Column name. Let's look at the data and see if it's inside out. Remember how you
Oh,
the name is different. So do you remember how
Really? So that would make me start as I see that.
names,
Oh, yes.
I don't know if you can use true. So it should take things exactly. You're not doing exactly. This is true all caps. You don't have all caps. So true. Mhm.
C makes a vector out of whatever object you put inside it. So it's built, it's just okay, you have
vector values in here. So it's like your C like or the vector are columns. No, that's one separate. If you could run the C parts outside of this, and it would still print it.
So then I'm trying to
Much online.
I think at some point somebody wanted to ask how to organize code in GitHub, but that might be a bit going to what.
Great question. I mean, yes, use GitHub. I'm not the person to talk about it though. Okay, we're going to come back together and go through this exercise as a group. I saw a lot of really great things from folks, and it looks like most everyone was making some good progress on this activity. I'm just going to start typing through. Feel free as I get to any part that maybe you got hung up on, ask any questions you might have about it as we're going. So first I'm going to read this data frame into our studio. I'm going to call it Hawks. I'm going to use the read.table function. File name, if I'm drawing a blank, as long as I have my working directory set well, then I can just scroll down with tab completion and find Hawks day 2 CSV. Let's see, does it have header names? Yeah, you have a question? Just because I'm using the read table function. It's just choice. That's what my notes say. Yeah. Okay, do I need to have a header parameter for this data file? I haven't looked at it yet. Did any of you look at it? Does it have column names?
Yeah.
Cool, then if it's column names, I want header equals true. What about row names? Did it have row names? As in numbers, right? Like labeling the rows uniquely. You should leave that one out then, if there's no row names. But since we need to read table, I do need to tell it how the file, that it's a comma separated file. When I run this line of code, and now Hawks has been generated up in this upper right corner. So it looks like that worked. What if we had put row names in there? I saw this coming up for a few folks. I'll say row names equals the first row. I hit command return. And I get an error down here saying there are duplicate row names not allowed. Well, so let's take a quick look at that file. I open up the file with Excel. The first column, those are the species names, and it's a factor, right? Those repeated species names. So we can't use that as a row name for this file. And furthermore, there's nothing to the left of that column. Whereas with the iris data file, there was something to the left of that column. There was the column of unique integers ranging from 1 to 150. So no row names here, command return, Hawks are defined. Okay, so now we're going to start defining these average values. Let's see. Yeah, I'm going to copy and paste my text from before, and then just change the important parts. So a command copy, paste. So I've got all these codes where I'm defining the average values. Instead of average setosa sepal width. I'll call this average.tail.ch for the Cooper's hawk, average tail.rt for the red tail, and average tail.ss for the sharp shinned. I have to change a lot of these parts where we're indexing objects. So we're still using the mean function, but it's not the iris data frame. This is the hawk's data frame, and it's the tail column. Make sure you spell hawks correctly. Hawks $, tab complete, species, age, sex, wing, weight, tail is what I want. And we're indexing by which hawks $ species are exactly equal to, this is the Cooper's hawk column, so I'm using CH for the Cooper's hawk species. Same with the rest, replace iris with hawks, replace sepal width with tail. Replace the which function, right? So real quick, I'll replace this versicolor with RT for red tail hawk. So right, we'll go inside out. So in this middle line here, I have hawks $ species. If I just run that highlighted piece of code, that gives me all of the species names in the hawks data frame. If I say hawks $ species exactly equal to RT, it gives me a true false vector where the trues are corresponding to where species entries exactly equal RT. And then the which function takes that vector of trues and falses and it spits out the indices for the true values. And the false values is just nothing returned. So if I do command return, now I have a vector of indices for all of the rows corresponding to hawks whose species names are RT. And so now we can use those indices to index the hawk's tail column and calculate the mean. There's hawks, sepal width replaced with tail, iris turns into hawks, species turns into sharp shinned. And we have means for each of those three hawk species groups. You have NA values. It means there may be NAs in your columns. Were NA values also experienced from other folks in calculating the means? So there could be, for some reason, an NA in that column, in which case you can add to your, for use of the mean function, the parameter na.rm equals true, and then it'll remove the NAs from the column when it calculates the mean. Okay. And then for adding these vertical lines for the tail means, we have to make this tail means data frame. I'm building a data frame. The first column will be called mean values. And its entries are, I'm building a vector out of the names for all of these mean values we just defined. So I have average tail.ch, ave.tail.rt, and ave.tail.ss. Close parentheses, comma. And then we define the species name column as ch quotes rt quotes ss.
So we will get NA values as well.
More folks are getting NA values. Where are the NAs popping up? Is it when you're calculating the means?
Yeah.
And did the na.rm part equal true? Did not solve it. If you open your hawks data frame and look at the names of all of the columns, is the species name species or is it I.species? Ah, yes, okay. So for some reason, with some of the different operating systems, when you're reading in CSVs and RStudio, it tacks on this I.. character into some of the column names. This did happen with another student. So when this happens, you can do one of two things to change it. One is you can change the names in the data frame. So we do names, hawks. If I just command return on that, it shows me the names of all the hawks. If I index this object with the square brackets and the number 1, then it gives me the first column name, species, and now I can change it if I wanted to. I could change this to the assignment operator. I can make it i.species. No, that's not what I want to do. I want to make it just species. So now I can change the column name in the data frame. And that should hopefully fix this issue. Alternatively, you could use that other column name in all of these commands where you index for those columns. Either one should work. Okay. So here is where, moving on, where we define the tail means data frame, so we can grab the average values for those tails. And then we have our call to the ggplot command. I'm going to just copy and paste our previous one. One of the smaller ones. Can handle the details later. Data, not iris. Now the data is hawks. Instead of x equals sepal width, I want x to equal tail. Fill is still species. Geom histogram doesn't change. Geom v-line doesn't need to change except for here where I define the data frame that we're using to make the vertical lines instead of means. I want this to be tail.means. Run this last call for the ggplot function. Oh, it said mean values not found. Oh, this is good. Okay, so I have an error. There's some, it tries to tell me where the error is, which isn't super helpful, whatever fun x index I is, but it says object mean values not found. So I need to go look for wherever I typed mean underscore values because I'm being told it's not found. So here, when I define the vertical lines, I have the aesthetic x-intercept as mean underscore values. That's supposed to be the column name from the tail.means data frame. So if I go back to where I define tail.means, I can see, oops, when I made the mean values column name, I put a space there instead of an underscore. That's why I'm getting this error. There's an inconsistency between the actual column name that I made and the column name that I told ggplot to look for when making these vertical lines. So I need to change one of those two things so they're consistent. I'll add an underscore and rerun the tail.means data frame command. Go back and rerun the ggplot command, and now, great, I have my graph, or at least the start of it. Yes?
When you make the data frame, I understand kind of like the grabbing values or the average scale of CH, but for the species, are you just making the CH onto the capital, like you're not pulling it from
Correct.
a data?
Yeah. I'm just typing in the species names exactly as they are in the Hawks data frame. In terms of how they're like spelled, capital RT, capital CH, capital SS, and then the order comes from. Okay, so this is fair. If I type Hawks $species, the order I'm using comes from the order of the levels for the factor. So R automatically identifies, so when we have these factor, we have these common groups of the species names. R says, okay, those common groups are the Cooper's Hawk, CH, RT, and SS, and there's an order to those names that R assumes, and it's usually alphabetical. So I'm trying to use that same order. Okay, any other questions?
I'm still getting
The NAs from the column name.
I had the people online rename it, and it worked. So I think that that's all.
So maybe attention.
Anyways, this will be as far as I go with continuing this example. There are a couple more steps I suggest you trying. The code that I'll send at the end of the day will have those last parts on it, but I want us to move forward from here instead of with this one, because from here it's the same. You're doing the same things, you know, modifying the labels, the title, the second legend, as we just did for the recap. Are there other questions though from folks before moving on? We're going to take a bit of a break from graphing and get into some more less visually fun things to work on. Okay. Oh, sure.
Sorry, if you wanted to add the like with flowers.
Mm-hmm.
For the flowers, you just wrote C, and then means $sign.
Yes,
values.
right.
For this one, I had to paste C middle values. Why?
The actual values?
No, just the values that I used. Like the top lines. In the,
These parts?
yeah, those.
These
So I
or
just copied and pasted C, yes. all of
this?
that in order to get those values as opposed to just doing C.
That's fine. One way or another, you have to point to RStudio or ggplot. Here's where these values are, and in the right order, and I'm giving the right number to coincide with the number you expect. You can do it by indexing the data frame and the column and using the column name, or you can do it by just providing them manually and just make sure they're in the order you want them to be in.
So how would you do it if you did
So we have to make another data frame like we did with the flowers. You have to do it for the hawk. So that's what this other data frame is for. Yeah, it's there's a phrase for this. Was it like half a nine, dime a dozen or something? 6 of 9,
6 of one, half dozen.
6 of one, half dozen of the other. Right, so you can either be just defining these really long vectors, objects inside of ggplot, or you can, outside of ggplot, make another data frame object, and then you just call them by name. So you still have to do, and again, the same amount of typing. It's just, do you want your ggplot code to look really long and potentially messy, or do you want it to be like compact and reference other objects that you've written elsewhere? Right, because yeah, enough said, I think. Okay. Other questions from folks? Oh, you have a new error.
Yeah,
Species not found. So this might be with the column names issue again. There'll be we're gonna have another short break and then ideally another breakout session in the end, and I can come try and look then. But I want to try have us move forward. So next part, we're going to talk a bit briefly about handling NAs and data, and so doing negative indexing and redefining factors. So don't forget to look at your data. Let's take a closer look at this Hawks data. I'm typing view and then parentheses Hawks to use the view function to view the Hawks data. And the first thing I notice is that in the column for the sex of the Hawks, there's a lot of empty entries, blank cells. Whereas if you scroll a little bit down in the weight column, row 14, there is an NA value. And you'll notice that the NA value there has been grayed and italicized. It means R recognizes that entry as an NA. It can handle it. It has functions for working with NA values. They're very handy. It doesn't have functions for working with blank cells. In fact, these blank cells can be difficult because we can't handle them in a convenient way because those functions don't exist. So it'd be convenient if when we read this file into R, we can somehow populate these empty cells with NA values so that it becomes easier to handle them later. Real quick, I forgot to mention, right, what are some of these NA functions we have available? So for example, there's a function called is.na, which literally asks, is this object an NA object? And then R will turn a true or a false. So if I type in here NA, which notice as soon as I type the capital A following the capital N, it changes font color, and R is now recognizing the pair of letters, capital N, capital A, as an NA object. Now, if I press Command Return on this is.NA use of NA, R says true. That is an NA, which is great. I think you can do this with a vector of NAs. And I get true, true, true. However, if I give this function something that's most definitely not an NA value, like the word cheese, it will return a false, because the character letters cheese are not recognized as this reserved object NA. So if you have a function that gives you true or falses on whether or not it's an NA, that's how you can systematically handle NA values in your data. So how do we populate the empty values with NAs? When we first read the Hawks data frame in, we have an option, there's another parameter in that function that we can use to try and specify NA value. So I'm going to reread the Hawks CSV file into RStudio. So I have Hawks, here's read table, parentheses file equals tab complete to get me the rest of the Hawks file name, Hawks day2 CSV. It has a header, there are column names, so I have headers equals true. It is comma separated, so I have sep equals open quotes, comma, close quotes. And the new part is we're going to add this parameter called NA strings. And if we use tab completion, we should be able to scroll down and find here NA strings. If I hover the mouse over it, I get a nice little paragraph of information about this parameter. So there's a character vector of strings, right? Strings, text words, which are to be interpreted as NA values. Blank fields are also considered to be missing values in logical, integer, numeric, or complex fields. Note that the test happens after white space is stripped, but that's less interesting. The most important part here is this first sentence. So we use this na.strings parameter. And we can provide R with a vector or a list, so to speak, of different entries to recognize as NA values. Right, another good example, maybe different people collected this data set, and because there wasn't a good standard protocol for recording the data, they all used their own favorite phrase for NA. Some left it blank, some used capital N, capital A, some used lowercase NA, some used capital N, lower a, capital N, like this, the whole, you can try and address this all at once. So we saw blank, so I'm going to use quote, quote, which means blanks get interpreted as NAs. I have a comma. I can also put in here, in quotes, capital N, capital A, and just make sure that that object will be recognized as an NA. We can also try and add in the other types of NAs we see people commonly enter, lowercase NA, or maybe the NaN object, or maybe someone decided they wanted to use N/A, in lowercase. Anything you can think of or that you've seen in the data, you can add into this vector if you want them all to be turned into standard NA values. So now I'll stop there and press Command Return. And now if we view the Hawks data once more, we see that all those empty cells in the sex column now have NA values in addition. Okay. Now, there's another nice function for NA handling called NA omit. It goes through your data frame and finds any row in which an NA value is present. It removes the entire row from the data frame. So it can really conveniently remove all the NAs, but you should realize that depending on the questions you want to ask, you may not want to use that function. For example, if you wanted to compare the wing, right, this is wing size, weight of bird, and tail size. If you wanted to compare these three things across age, and we have all these age entries, we don't care about the sex of the bird, then maybe you don't want to remove all of the rows where there's a missing value for sex, because then you're going to just remove some of the data where you have entries for age. Yes? Sorry, complete what? I'm not familiar with the phrase complete case analysis. So like if I want, like if I ran a function on the data frame and there are NA values in it, does it automatically handle them? Like when you read it into RStudio. Okay, yeah, like so it's like if it's a capital NA, like in the CSV file, that gets interpreted as an actual NA value. Everything else is different. Okay. Okay, sorry. Okay, but yeah, so anyways, that's the warning with any omit. Is that it really does just any row that there's an NA, it removes that row altogether. And so if you do want to have those removed because you want to like maybe split your data by the sex of the hawks, then you could use it. But if you didn't care about the sex of the hawks and are just looking at age or species, then you could lose a bunch of potentially useful data because you're removing all these parts where you have these NAs for one column but not for the others. We're going to go ahead and NA omit very liberally now and just remove every row that has an NA in it. So I'm going to call this hawks.trim because it's a trimmed version of the data. Use the assignment operator and the NA omit function and put inside of that the hawks data frame. And then I want to make sure, so here we can see that the hawks data frame has 908 rows in it. After I run the NA omit function, the hawks.trim data has only 327 rows because there was a lot of missing data in that file. But now, if you look at hawks.trim, there's not a single row with any missing data. And so this is the, we could factor this data set by any of the categorical variables and not have any issues.
So if you were interested in satisfying like the sex and the other qualities, you have to use this data frame. You can't use the other.
Yeah, because so in the other data frame, there's so many missing values in the sex column that if you were to try and factor by that, you'd have differing numbers for that group, but you'd have fewer numbers for the sex column than you would have for the age or the species columns. And so, yeah, unless you want to get into methods where you're comparing different size groups, which exist. But I'm not saying anything else about that. Okay. Now what? Let's re-examine this last part, refactoring, negative indexing. Right, okay. Let's look again. Oh, I have a graph up. That's fine, great. Let's re-examine the Hawks graph we ended yesterday with, except we just made that graph earlier. I'm gonna grab this ggplot command from before. Use it again. It's the same graph they already have displayed. And the important point is there are so few Cooper's Hawks in here compared to the Sharpshin and the Red Tail. So what if we wanted to remove all the Cooper's Hawks from this data set, because there's not that many to begin with. Is the preface for this next activity. If we want to see exactly how many entries there are for the different categories, we can use the summary function on our data frame. And the summary function, sorry, hawks.trim, return. And the summary function shows us that, okay, it gives us the quartile information for the continuous data columns, wing, weight, and tail. And it gives us abundance values for the different categorical columns. So the number of males and females, the number of A's and I's in the age. I'm blanking. I must be some phrase for not an adult. Infant. That sounds good to me. Infants and adults, although if you graph that age column, then there are some people who did not know what infants were when they measured them. Anyways, species, there's 68 Cooper's Hawks, 4 red tails, and 255 Sharpshins. So let's remove those 4 red tails from here. So in order to remove them, we have to find out which ones they are. So I'm gonna use the which function to find the indices for which Hawk's $species, oops, there we go, are exactly equal to RT for red tail. So press command return. Whoops, be careful, don't forget that we're using the Hawks.trim data frame, not the Hawks data frame. There we go. So from this any omitted data frame, Hawks.trim, there are only 4 red tail species, and we have now their rows 127, 162, 63, 64. I'm going to save this object so it's easier to call again later. I don't have to keep typing that whole function. So I'll call this rt.rows equals copy paste that previous use of the which function, command return. Now I've saved those rows as a vector called rt rows. Now to make sure that this indexing from these rows gives us in fact those 4 rows for the red-tailed hawks, we can actually just index the hawks.trim data frame by the rt.rows. I want to see all the columns, so I'll press comma and then just leave the column entry blank. All right, so I'll see the rows corresponding to the red tails in all of the columns. Press command return, and this is printed in the console. So excellent, I have in species, they're all red tails, and then the rest of the pertaining information regarding age, sex, wing, weight, and tail for those 4 individuals. So now to remove them, we're going to use negative indexing. Right, so if regular indexing gives me the object that's in that cell, negative indexing gives me everything but the object in those cells. For example, if I type hawks.trim square brackets to index minus rt.rows, comma, for all the columns, and run that, then I'm going to be returned every single row in the data frame except for those 4 corresponding to the red-tailed hawks. Means if I now want to actually remove altogether those rows from the data frame, all I have to do is assign this object to a variable name. And then I'll now have a copied version of the data frame where we've removed the 4 red-tailed hawk rows from the original data frame. So I'm going to copy this negative indexing use and make a new data frame that we can call hawks dot no RT for no red tails. Use the assignment operator, paste the hawks.trim where we're indexing with minus the red tail rows, press command return, and now you'll see in the environment we have the hawks.noRT object, and it's got 4 less rows than the hawks.trim object does right next to it. Let's check to make sure that it worked. We'll use the summary function. It's hawks.noRT. Press command return. Uh-oh, okay, so this kind of worked. We have here in the summary, we see in species, there are 0 red-tailed hawks, but it's still recognizing the fact that the red-tailed hawks used to be in this data frame. What's happening is, remember, we have the objects of factors, right? The species here, they're a factor. When we first defined the hawks data frame as a factor, red tails were there. They were one of the factor groups, one of the levels. Even though we removed all of them, they're still recognized as one of the levels in this group, which means anytime we use this factor to do things like maybe make a graph, we're going to be given a legend spot for the red tails, even though there's no red tails in the graph, because there's no red tails in the data. So to fix this, we have to redefine the species column as a factor that doesn't have the red tail level in it. Okay, so how do we do this? So we're going to redefine this column. So we have hawks dot no RT $ species. And if I just ran that part alone, right? We get printed all of the species, the Cooper's hawks and the Sharpshins, and then we're shown the levels, CR, RT, and SS. Right there again, we can see RT still being remembered as one of the factor levels. So I want to change this, so I use this hawks.noRT species. We're going to reassign this object, so I have the assignment operator. I use the factor function, which is what we use to make factors in the first place. If we're not given them already. If you want to make a factor function, you provide the function two things. You provide it the vector that you want to factor, and then the objects you want to factor it by. So the vector I want to factor is the hawks.noRT $species column. And the levels I want to factor it by are just the CH and the SS levels. If I leave out the RT label, then it won't factor by RT, and then it won't have RT showing up with a 0 next to it every time we run summary. And here's where I could change the ordering if I wanted to. If I wanted to have Sharpshind first, then I could type Sharpshind and then CH, and that would allow me to change the ordering also in the legends. So command return on that line. Summary of the data frame, hawks.noRT, command return, and now we can see under the species return result, we no longer have RT showing up with 0 entries. It's been removed altogether from being considered as part of the factor of species. So let's regraph our data. Copy the ggplot command from before, paste it beneath, change that, remember data, we're graphing hawks.noRT. I don't want the vertical lines here because that when we did the vertical lines, that was when we had 3 groups. We haven't changed the other data frames, so I'm just going to leave that out for now. We're just graphing the histograms. So I only have these 2 lines, highlight, command, return to make the plots, and excellent. We only have the 2 groups, red tails are gone, and they're not showing up as objects in the legend either. So we've completely removed them from the data and from the factor grouping. Okay, any questions from folks? This is kind of like a short little interlude onto a couple other aspects of working with data frames, NAs, negative indexing, redefining factors. Okay. Excuse me. Okay, next part. Graphing 2 continuous variables and using the logical AND and OR. So we're gonna get to see how to make like scatter plots, XY point plots, and then use that as motivation for exploring another aspect of using logical commands. So let's see, so far, let's use our scripts. We have examined ways to visualize and analyze one-dimensional variables at a time. Sometimes you're interested in 2 variables at once. For example, what might patterns exist when looking at the tail and weight of a hawk? So, common way to look at 2-dimensional data is with XY scatter plots. How do we do that with ggplot? So again, as before, we have our initial ggplot function where we say we're going to graph the hawks data, and I'm going back to, no, sorry, hawks.trim data, sorry. And the aesthetics, so now, excuse me, we specify both the x-axis and the y-axis because we're going to be making 2D plots. And so we have to basically help tell our studio from the beginning, these are the axes for data we're working with. So x equals weight and y equals tail using the column names from the hawks.trim data frame. Plus, now I get to specify the type of graph I want to make. I want to make a XY scatter plot, so I use the geom_point function for point plotting, and that's it. Highlight these 2 lines, press Command or Control Return, and now we have a scatter plot of tail versus weight with a bunch of small clusters in the points. So we'll talk a little more tomorrow about some of the other fancier plotting options in RStudio, both for other options for one-dimensional plots and also options for two-dimensional plots, like the clustering functionality that's in our PCAs. Yeah, but we can also just sort of quickly guess at what these differences are. After seeing the categorical variables in our data frame, we have different species, so we could have grouping from the species. We're supposed to have different ages, but I kind of let the cat out of the bag that those ones didn't make a lot of sense, at least to me, naively. But then we also have sex for the hawks. And so these differences in bird mass and bird size may well be correlated with also just the sex of the birds. So we can color the points by these different categorical variables. We can also change the shapes of the points by these different categorical variables to try and tease out some of that information. So if we want to color by species and change the point shape, we'll change the shapes by sex. Then this is similar to before, where we just start modifying aesthetics in the point function, the geom point function, as you did with the histogram. So I highlight and copy the command before, paste it below, and now I'm just typing inside geom point using the AES parameter and setting color equal to species and shape equal to sex. Highlight both lines, command return. Yeah, great. So R automatically picks colors for us and shapes as well, just based off of like the first values that it has to use. So we can see in the graph grouping by species. So the bottom left are all the sharpshins, the middle are the Cooper hawks, and then in the upper right's mostly just the red tails. And then there's some splitting also by sex, as denoted by clusters of circles versus clusters of triangles, where the triangles are typically in the lower left of the pairs and then the circles in the upper right. We could also use the age parameter instead. So let's highlight this command, paste it below, and we'll swap out species with age for color and swap out sex for species for shape. Highlight, press command or control return. And so now we're splitting colors go by age and the shape of the points go by species. So we have squares in the bottom left for the sharpshins, circles in the middle for the Cooper's hawks, triangles in the upper right for the red tails. And then here's where the age, this is why I'm kind of suspect about the age measurements. They're kind of mixed. They don't really seem to go with the splitting of the grouping in this data. Yes?
One question about saying they only saw 2 species. Is anything coming to you as a solution?
It sounds like they used their data set that didn't have the red tail species in it. So the question was,
when I tap it,
yeah. Yeah, so this is why I went back to using the one where we remove the NAs but not change the names. Was that?
For some reason, it's
You saw, okay. Do you mind? Thanks. Let's see. For what we're logicals, NAs. You could try doing this next part with just the first data frame. Let's see. Right, okay. This is the 2D plotting. So going on to some mixed logicals. So suppose you wanted to make comparisons within these different groups. you wanted to subset your data and identify which rows are adult birds and Cooper's hawks, or infant birds and sharpshins, or male birds and red tails. Right? You have these two conditions you want to search for, not just one. And it extends. As soon as you can do two, you can do as many as you want. But the point is, we'll focus on two. So this is where we use what are called logical comparisons, or the and or operators. The idea here comes from thinking about what are called truth tables, and the ideas of, okay, we have a true statement and another true statement. In total, that makes one whole true statement. So for example, if I type true and I use the ampersand sign, which is R's symbol for adding two true or false statements together. So I have true and true. The logical and operator, the rules of that mean that true and true, that's a true statement. You give me two true things, so therefore that is a true thing. If one of those were false, instead, so I have true, ampersand, there you go, and false. Any guess as to what the result of this statement will be? False, yes, right? So the and operator is saying both of these things need to be true for the whole thing to be true. So if one of them is false, the whole thing is false. So press command return, and I have false returned when I try and compare a true and a false statement with the and operator. Ordering doesn't matter. If this is false and true, there you go, false and true, then I still have an overall false statement. And we don't count double negatives when we're doing logical operations. So if it's false and false, it is still in total false. There's nothing true about that statement. Now, the or operator gives you a little bit of flexibility. It's less restrictive than requiring both statements be true. It just requires that one of the statements be true. So if I do true, and this is where we get a little tricky, the or symbol for R is the solid vertical bar. For me, it sits right above my backslash. It may be in another location for other folks in your keyboards, but note that it is most definitely not a lowercase l or a capital I, depending on your font. You'll know that you've also got it though because it's another recognized operator, so its font color changes as soon as you type it. It doesn't look like typical text font. If we do true or true, again, this is a totally true statement because in this case, we only need one thing to be true, and we have both. If I do true or false, this isn't totally a true statement because we have at least one true statement within the whole statement. We have true. As before, order doesn't matter. So if it's false or true, we still have a totally true statement. And again, we don't count double negatives, so false or false is also a false statement. Okay, now this might reasonably seem totally abstract and ridiculous. The point is that we use these statements to help us subset and index data. So with some application, let's see if this, like, oh, that's why. So we're gonna subset the hawks data for female sharp-shinned hawks. So we'll do this in parts. One is we have hawks $species double equals to sharp-shinned. And if I just run that command alone, I get a vector of trues and falses, right? The trues correspond to which species names are SS, and the falses correspond to everything else. I can also type now hawks $sex equals capital F and run just that line of code, and I get returned another vector of trues, falses, and NAs. Oops, sorry. I need to be using the hawks.trim data frame for this so that I'm not comparing NAs with trues and falses. Okay. So right, hox.trim $species equals SS, vector of trues and falses. Hox.trim $sex equals F is vector of trues and falses. And so now I have these two different vectors with trues and falses in different and similar locations. So if I want to find all the cases where I have both female birds and sharp-shinned birds, I can use the logical AND operator to search through all those vectors and find all the cases where both entries are true. And then we found a bird that is both a female and a sharp-shinned hawk. And we can do it all in one line. We can type hox.trim $species equals SS, and then use the AND operator and type hox.trim $sex equals F. I tend to encapsulate these in parentheses when I do this. I don't think in this example it really matters, but sometimes maybe your condition statements, they're not on categorical variables, but they're on continuous variables. So you have something like, you know, column X less than or equal to 10 and column Y greater than or equal to 5. And the parentheses at least help keep track of, I think, order of operations, so that logical doesn't get mixed up. Anyways, it doesn't hurt to have them in. So, so this will do the logical comparison for us, going through both vectors all at once, and should return in the end a new vector of trues and falses corresponding to where we have the trues are for cases where both the bird is both a sharp-shinned and a female, and the falses is anything else. So now I can put all of this inside of a which function to get the indices corresponding to the rows for these trues. And then I can put that entire command as my indexing object for the hox.trim data frame. Remember, data frames are two-dimensional objects. We have rows and columns. So at the end of this rather unsightly which function, I'm going to add a single comma and a space to make sure that I'm still accessing all of the columns of that data frame once I've indexed by all the rows that I want. And if I press command return on this line, what is printed to the console as output are all of the rows from the data frame where we have sharp-shinned hawks that are female, as data is given by the SS and the F entries altogether. Okay, and then if we wanted to save this object to use later, then we just assign it to a variable name. I'll call it F and SS Hox, and use the assignment operator. And then now this is a data frame that I can interact with easily by name up in the global environment. That's to make sure that I get all of the columns. So we're indexing, right? Everything inside the square brackets is indexing the hox.trim data frame. And so this which function is indexing the rows, and then we need two entries, because since the data frame is two-dimensional for rows and columns, I need another entry to grab the columns that I want. And if I leave it blank, that means I get all of the columns that are present. If you wanted to subset on a, oh, yes, we could use the OR condition to get all the birds that are either female or sharp-shinned hawks. So in this case, it's the only thing we change is you go in and swap out the ampersand symbol with the vertical bar symbol representing the logical OR. And we could run that command. Oops, sorry, I meant to rename that one as f.or.ss as opposed to f.end. So we have these two different data frames. And now you'll see in the environment, the AND data frame where it's female and sharp-shinned is 132 rows. When it's female or sharp-shinned, we have more because we've relaxed that condition, so there are more cases that are allowed. And here They are only present if they are female or sharp-shinned. So there are some cases where the species aren't sharp-shinned, but the sex is not female. For that example. Okay. Any questions from folks on either scatter plot graphing or the logical and or operators? Okay. Brings us to loops, if-else statements, and functions.
Is there any reason why that
there's-
line would return 0 observations in the variables, but it's meaning nothing matches?
It does, I think that means, yes, nothing matches. But it could be, right, it's nothing matches for whatever they asked R to look for. So there might have been a typo in what was entered.
Oh, yeah.
Okay. Right, okay, so this is the last new thing we're learning today. We're going to talk about loops, if-else statements, and writing our own functions. And then we will have, ideally, I believe, some time for our last breakout session, 9:30 to 12. We're going to go straight through, since it turns out we only have 2.5 hours for the class. Yeah. Or we take a very short break. Let's let you folks decide. You're the ones sitting through this. Hands for a 5-minute break. We'll just do it now versus hands for we just roll on through. We're going to take a 5-minute break. Thank you for voting. Good. We'll start again at 11:15 on the clock wall. All right.
No.
Yeah, problem is really this.
Yeah, so we want to change that.
I will change it here. So when the average works.
Oh, good, good. Okay, the next part's work. Okay.
At some point when I had to call the species following, it didn't appear my column.
It was looking at another one.
No, when I got like daughters, so my species is not in the options.
Yeah. Well, so did we rename this data frame or just the other data?
I renamed it just once.
So it might just, so that might be the issue is that we only renamed one data frame, oxygen, not oxygen.
Okay, so I have to rename it here also.
Oh, although if you run that, that should work. You rename ox, you said. Yeah, try running that one again. So, because that redefines ox.trim based on the original ox.
So if I
No, let's just view it real quick.
this one,
Ox.trim. So if you view ox, no, this is Oh, very strange. It's not. Okay, so we definitely have to rename that column. For some reason, it didn't rename the previous one. We try where is the spot where you changed, you renamed the column? Right there. Okay, let's run that one. Okay, now let's view that. So perfect. So that one's changed. Now let's try redefining constant trim.
so down
need to run that once more. Yeah. Okay. So now let's look at that data grid.
Wait.
Perfect. So now it's going to change. So might have just been missing the having to go through each of the previous lines. And it's tedious.
Okay. Okay.
But
So now
that
it's
should,
correct.
yeah.
And what we can do is try to change the color.
Go for the plotting part. I can scroll that back up if you want. Oh yeah, just like here. We have this part. Just yeah, you can do that. Perfect. Coffee in the hallway. Very strong, bitter coffee. Okay, we're back at 11:15. Let's continue. So loops, if-else statements, and functions. We're getting a little more into the technical side of some programming. We're still going to try and do this through the context of looking at data and analyzing data. But I want to try and emphasize that these, as with some of the previous things we've done today, these are pretty general aspects that you may be using in many ways. So loops. Sometimes we may need to perform operations multiple times, and basically the exact same operation many, many, many times. And you don't want to just, tweak one parameter, rerun the code yourself, tweak the parameter, rerun it again, and copy and paste and have the script file that has 500 instances of the same code with just one thing changing. Instead, we can write a loop, which takes that common segment of code and runs it over and over and over again, and it just has a variable that changes that represents that parameter for every time you run the code a new time. These are called loops. Good for generalizing a procedure and repeating it until you reach some kind of stopping condition. So we're going to talk about for loops. For loops are one of the two types of loops. So that's why this is not making sense when I look here. I'm on the wrong page. Perfect. Okay. The idea with a for loop is that we do something. We're going to iterate from a starting value to an ending value. So it's like for some variable from start to finish, run this chunk of code, and yeah. We'll talk about the other kind of loop once we actually see what this loop looks like. So to do this, we're going to make a vector that we're going to loop through. So I'll call this just a.vec for a vector. Assignment operator, C function, and values 1 to 10. Command return. So now we have a vector that's going to serve as this object we're going to loop through. Now, I'm going to define an empty vector, so to speak. It's a vector full of zeros, because what we're going to do is as we loop through this A vector, we're going to do some kind of mathematical operation on its entries, and then save the output in another vector. So I want another vector that already exists, so I can easily just replace the values in that vector with these new values I generate during the loop. And I might as well make everything in this vector 0. So to make an empty vector in R, I'm going to call the vector bvec for b vector, the assignment operator, and I use the function mat.or.vec. It's a recognized function that allows you to, quote unquote, initialize matrices or vectors, or make these empty matrices or vectors that are automatically filled with zeros. To use this, I want, this works like we're indexing. So if I want a vector with 10 rows and 1 column, right, a vector, 10 rows, 1 column, that's a vector, then I type 10, 1. And then the mat.or.vec function will give me a vector with 10 rows, 1 column full of zeros. If you wanted to make a matrix, for example, a 10 by 10 matrix full of zeros, then you'd put 10, 10 in here. Okay, so run that line for the 10, 1. And down here in the environment, you can see b.vec, numerical 1 to 10 entries, and they're all zeros. So now the for loop. So I start off with typing the word for. That's a recognized trio of letters in R. It says, oh, great, we're going to write a for loop. It changes the font type to blue. I add a space, and now in parentheses, I type the phrase I in 1:10. Close parentheses, curly brackets, and press return inside the curly brackets. So now I have the for statement that initializes and says we're going to do a loop. We have in parentheses the statement, the variable I, which is going to serve as our dummy indexing variable that we use to allow us to access the different entries in our vectors. And then the next is the in, is another recognized object. That's where we say, okay, here are the values we're going to loop through, the start to finish. And I'm providing specific values going from 1 to 10, and all the numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But if you wanted to do something different, you could use some other function. You could do 1 to n rows of a.vec, where you use the n rows function to determine or calculate the number of rows that are in that object if you don't already know. I know it's 10, so I'm just going to type 10. And then these curly brackets, these define the operation that happens as we run through the loop every single time. So for example, I could use the print function, which prints output as like a quoted string, a character. And I could just have the print function print the statement in quotes, this is iteration, and then outside the quotes, can I just add an I like that? Shoot. Sorry, I'm trying to skip a bit so we have a little additional thing. Oh, I know. I'll add just another print statement. One print statement for the quoted phrase, this is iteration, and then underneath that another print statement where I'm going to print this variable I during each iteration of the for loop. So we can visually see more what's happening. I'm going to run these 4 lines of code. So highlight all 4, press command return, and now in the console, we can see repeated statements been printed. Of course, we have the phrase, this is iteration and the value 1, this is iteration and value 2, iteration 3, 4, 5, 6, 7, 8, 9, 10. Right, so every time this loop runs, right, so at first, what it's doing is it's taking this dummy variable I and it's setting it to equal a different value for each iteration of the loop. So at first, I takes on the value of 1 because we're starting the loop at the value of 1. And then everything that happens inside of the curly brackets happens under the assumption that I equals 1. So we print the phrase, this is iteration, then we print the value of I, which is 1. We've reached the bottom of the code inside the for loop, so we go back to the top and start again. But before we start it, we take the value of I and increase it to the next value that we've defined in this 1 to 10 command. So I goes from 1 and then takes on the value 2. And then we rerun everything inside the loop. We print the statement, this is iteration, and then print the value I, which was 2. We hit the bottom, go back to the top, change the value of I to 3, run the code again, hit the bottom, go back to the top, change the value of I to 4, run the code, right? It's iterative. Sorry? Object I not found. Is I in your first line in the for statement, you have 4, and then in parentheses, thanks, Don. Okay. Let's see. In progress. Cool. Syntax?
Yeah, always good to just duplicate exactly what's on the book when declaring there.
Great. Okay. Next example. So we'll do more than just now print some words. We'll do this operation. So we'll just add another for loop. For parentheses I in 1 to 10, close parentheses, open curly brackets. So we're going to assign to the ith entry of the bvec vector. So I'm indexing it by the value I using the assignment operator. I'm going to do an operation on the ith element of avec. I'm going to index a vector by the value I. So I'll take that entry and I'll add the value of 2.3 to whatever the value of the a vector I is. And then while we do this, I'll print the value of bvec indexed by the value of I. And actually, we'll print it both before and after we do the operation. So we're going to print the value of bvec I, we'll do this operation, and then we'll print the value of bvec I after the operation's been done, and then that's all we have inside of our for loop. So we'll now run this whole loop. And now print it out in the console. We have a whole bunch of zeros, right? Because every entry in zero starts in the b vector starts as 0, and then we have the first entry that goes into bvec is, okay, what was that first value of a? Well, this a vector are the numbers 1 to 10, so we took 1 and we added 2.3 to it, and so that's why we have 3.3 for this next entry in the bvec value in the b vector. And then we finish, go back to the top. I now takes on the value 2. So now we're indexing for the second element in these different vectors with the value I. And then so we grab the second entry from avec, which is the number 2, add 2.3 to it, and so we have 4.3 for what goes into the bvec vector. Okay, this is a slightly like kind of contrived example for loops, but it's done to try and hopefully drive more of the point. We'll do a more concrete example in just a little bit. But are there any questions at the moment first about loops? Yes. Bvec twice. Oh, just to show that in each of these iterations, it starts as 0 and then we change it, and so we can see what it looks like after we've changed its value. Yeah, we just don't run this print command. We're not storing the zeros there. We use the print command just to see what's happening during any iteration. If I hid the print command altogether, I could run this line and it prints nothing. It just says, cool, I ran the for loop and I've now changed the values in B vector as you asked me to. I just didn't show you anything along the way. You don't actually have to put the print statements in the for loops. I'm doing it here, one, because I like to think it's instructive. Two, if you're troubleshooting for loops, print statements are an incredibly useful tool for troubleshooting for loops. Because typically when you run a for loop and you get an error, the for loop stops and all you see is the error statement just says, we ran into an error. And then usually your next question is, where in the loop did the error occur? I don't know. So if you have a print statement in here that just says print I, and yeah, why not? We'll make avec equals c 1 to 5 and na, no, call it cheese, not cheese, and 6 to 10. And so I've put a character in the middle of a vector. Let's try and run this for loop. Aaron, avec I plus 2.3 is, oh, this is a bigger problem. This is what happens when you try and come up with examples on the fly. The whole vector is a character vector now. Not a cheese, sorry. NA. Tell me that works. Trying to force an error. It's not working. Okay, well, the point is, when you have the print statement, it prints the value of I. So if an error occurred and terminated the loop, it would stop, and the last thing we would see is the value of I that was printed when the loop was terminated, so we can diagnose where that error occurred in the loop, which entry in our vectors is causing an error to occur. Yes? That gets stored into bvec.
Yeah.
From was it this part, this print b.vec.i?
This before you hatchback comes out.
Yeah.
It's exactly.
Did you run it more than once? Yeah. Right. So once you've run it, we've now changed the values of bvec. And so, right, like so here, my b vector has been changed. It is the new values, there's NA in there, but whatever. So if I ran this statement and I have the print bvec, do the operation print bvec, I will also have that same thing happening because the value of bvec to start with is 3.3 because I've already run this loop once before. We've already reassigned the values. Okay. Right. You don't always need loops. They can sometimes be slow. Some of these operations can be done just with simple math. For example, if I just take a.vec and add to it the value 2.3, press command return, what I'm given are all the numbers of avec with the number 2.3 added to it. So that's an example where it's called a vectorized operation, and it recognizes that you want to add 2.3 to everything in this vector, so it just does that. You don't actually have to write the loop. It is possible that using loops may be slower than using these vectorized operations. On the other hand, if you wanted to generalize a more complicated routine or task, like looping through a directory of files and reading them in and making graphs of them, that's something that would feed nicely into a loop structure. You don't really have mathematical operations for doing that kind of procedure. and is the example we'll try to get to soon. Okay, if-else statements. Another important functionality are called if-else statements. They're logic-based statements that allow us to perform certain operations as long as a specified condition is met. If condition 1 is met, then perform condition 2, else do nothing or perform condition 3. That's the idea behind calling them if-else statements. Typically used as part of a more complicated procedure. As an example, let's suppose that all of the Setosa sepal widths were accidentally measured in millimeters and we want to convert them to centimeters. So we're going to write another for loop, and we'll put an if-else statement inside of this for loop. We should still have our iris data set read in. Good. So first what we're going to do is loop through all of the rows of the iris data frame. And anytime we reach a row where the species is Setosa, then we'll divide the sepal width by a value of 10. So there's our if statement. If for this row, the species name is Setosa, then do something, then divide the sepal width by 10. So first the loop for, what's all this? That's fine, doesn't matter. Okay, let's do it for, parentheses I, in 1, 2. Oh, I don't remember the number of rows, so I'll use the function nRow for the data frame iris. So R will just calculate the number of rows and then fill that in. So it's going to run from 1 to the end, the number of rows in the iris data frame. Close the parentheses, open curly brackets, return. Now everything I want to do in the loop goes inside this part. So our if statement starts with if, parentheses, right? I want to compare the species in the iris data set. So I'm typing iris $species. And I'm indexing this column vector by the value of I, because I want to loop through all of the species names and compare them to another name. So I've indexed the iris $species by the ith value for my loop, and I'm going to set it, or not set it, I'm going to compare it to the name Setosa. So this will return true or falses, depending on whether or not the species name is in fact Setosa. And when it's true, the if statement will say true, and then it'll do what we want to do. So to write now the condition of what we do, if the operation that we do if the condition is true, I add another curly bracket and press return. And now I'm writing down the operation to perform for when my if condition is true. And that is dividing the value of sepal width by 10 and saving it as a new value of sepal width. So I'm taking the iris sepal width column, indexing by the value of I, and I'm reassigning it the old iris $sepal width value, indexed by I, but now divided by 10. And so I take the old value, divide by 10, and set it equal to my new value. This is what we call reassignment. And while I'm here, I might as well add a print statement so I can notify myself that our if condition ran true and executed. So I'll add the print statement that says, found a Setosa. So I at least know that something is happening. Now, we can also write in for R to do something for scenarios when the if statement is not true, when it's not a Setosa. To do that, we use the else command. And again, another set of curly brackets. Press return. And now I can have some code to execute for any time this if condition is not met, anytime the species are not exactly equal to Setosa. I'll just put in here a print command that just says not a Setosa, but you can put anything in there. It could be a whole other operation to perform of any kind. Okay, let's highlight and run this block of code. Press command return. And we're done and streamed to the console are a whole bunch of printed statements of not a setosa, not a setosa. If I scroll up, I'll eventually find the section where we had setosas. Here they are. Setosas were found, so those sepal widths should be a factor 10 smaller than they were before. We've converted those values by 10. The original file, well, not staved. We didn't change the file outside of it. This is all working inside of RStudio only at the moment. Yeah. The iron brackets right here. Yeah, right. So we're indexing. So in this for loop, we want this if-else condition to be on a given row in the data frame. So I have to index the data frame to access that row. And as soon as I'm done comparing one row, I'll move on to the next row. That's the looping part. So that's why I'm indexing the iris species column vector by the variable I, which is our looping variable. It's a variable that changes values as the loop iterates and progresses from one round to the next. Yep. Yeah, if it wasn't setosa, it didn't. Yep, exactly. Yes, if we run it again, we'll divide by 10 again. If we look at iris real quick and the setosas, the sepal widths, okay, they're factor 10 smaller than they should have been. They used to be 10 times the size. We'll run this once more. Press command return, look at the data frame again, and now they're 10 times smaller. So yeah, it'll totally do it all again. Okay. Let's see. However, you should realize real quick again that this is also a command that doesn't need to be done in a loop. We wrote a loop to sort of complicate the task of indexing a lot of values. We could have done this using which statements as we have in the past. So real quick, just to demonstrate that, we have iris $, sepal width, indexed by, oof, too many brackets, indexed by a which function. We're inside the which function. We have iris $species equals setosa. So here we already perform the if statement to find all the species equal to setosa. The which function helps us identify their indexes. We can index and grab all the sepal with numerical values that correspond to those rows, and we can reassign them to new values using the assignment operator. And I will copy and paste this previous statement. So we have, okay, again, all the iris sepal width values corresponding to species equal to setosa. And now to correct my data, I'm going to multiply by 100 instead of dividing by 10 twice. So I can run that line, and that performs the same task as the loop and if-else statement did. Now my sepal widths have gone back to the previous value they had. Right, just to demonstrate again, these loops and these if-else statements, they're great, powerful things, but you don't always need them. You might be able to get away without using them by just using the appropriate type of indexing and vectorized operations. Okay. Any questions there before we start talking about functions? Okay. We'll see about breakout time. All right, so functions. Unless, actually, how much? Modify the function, modify the function, modify the loop in the function. Yeah, okay, that's okay. We need functions for this, so we may not get to our breakout time today. We'll see. If not, we'll just start again tomorrow with it. Okay, functions. So, as you noticed, we are using functions that have been written in R all the time. And that's great. There's lots of functions. And you could find, if you wanted, the source code for those functions. They would look like .r scripts like we have. You could open them. Wait, these are files. You could open them like one of these scripts and there'd be a whole bunch of code in there that looks not unlike the code we're writing. Which is to say we can write our own functions and then use them to do operations later on, which can be an advantageous task. So let's write a function. Our function is going to take data frames and it will plot a histogram for those data frames. But it will only do so depending on whether or not one of the column names in that data frame is the word blue. This is a combination of semi-contrived, semi-applied exercise. So in the data that I shared with you in the zip file, we have a folder called data files, and there's 20.csv files in there. And these files have 2 columns of randomly drawn, normally distributed data. And the column names are blue and black in some of the files, and in other files, they are also blue and black. They are green and yellow in the other names, right? So we have some condition that varies between these files, so we can kind of simulate the environment in which we might be looping through data and doing something to the data depending on what is in the data we have. And the function is going to automate that task for us. Maybe it's not 20 files, maybe it's 1,000 files, and we really don't want to sit there with a mouse opening every single file and checking on these things and making the data one at a time, but we'd like to just loop the process and make it automatic. And a function all at once. So our function, we will call this my plotting function. That's the name of the function. We do this just like we're assigning a variable. We type the name of the function, use the assignment operator, and we type the word function, which is recognized as an R object. Font color just changed to blue. And in the parentheses, we define the parameters that we want to use in this function, the arguments for the function. I'm going to have a data frame parameter, which is just a name to represent the object that's going to come in as a data frame that we'll use. And then also the plot name that we're going to use as a variable later on as well. So these are temporary variables. They're not variables that exist in our actual environment that we work with. They just represent variables that we will have and use later when we run the function. And RStudio will nicely, well, we'll revisit that idea a few times. Okay, so we've defined the function parameters, close parentheses, open curly brackets. Now everything that the function is going to do goes within the curly brackets here. It's all put in quotes. This is our function that takes CSV files as its, quote, data frame argument. And if the column name is blue, then it makes a histogram of that column. Okay, so first thing we need to do before you can make the graph is check to see if the column name is blue. So that's where we use our if statement. If, parentheses, we want to check one of the names of the columns in the data frame, so we'll use the names function on the data frame argument name. We're checking for the column name of the first column, not all the columns, not the second column. So I'm going to index the names data frame object with a square bracket and the number 1. And then check for exact equality, so 2 equal signs with the word blue. And then we close the parentheses. That's our if condition. If that's true, then we make the graph. So now I have my curly brackets, return, and now I have the ggplot command to make the graph. And it's not going to be a fancy graph. We're going to just make a very bare bones graph so that this part of the code is relatively clean. I have command to ggplot. The data we are working with is the data frame that we feed into the function. So we use our data frame argument, comma. For the aesthetics, okay. The x-axis in our plot, x equals, it's going to be the column that has blue as the name. That has to be true because that's our condition to even get to this point in the first place. So I can just type blue for that column name, not blues 9, that's the color palette. Close parentheses, plus sign, return. And now I have the geom underscore histogram function call to make the actual histogram. And I'll just do 20 bins. They're all going to have 20 bins. Maybe some of them should have less, maybe some more. That you can suss out later. The point is now we'll just give them all 20 bins. Also, so we can distinguish them from one another, we'll give each one a different plot name as its title. So I'll use the labs parameter to change the labels, specifically for the title, and set it equal to the plot name argument that we provide to the function. And that's it. I don't have any else conditions for the cases where that column name's not blue, and I don't want to do anything else. So that's all we're going to be doing with this function. So I can highlight all of this code, press Command Return. That function has now been defined. It exists within our global environment. We can scroll down to the bottom of the environment. It starts as data, then values, and then functions. And any user-defined function, functions that you've written and executed inside RStudio are then provided here and listed. You can click on this, and it opens up a separate window to show you the code that comprises that function. Okay, let's test run this function. I need to set my working directory to this location where I have all these data files. So I have, for me, I need to now, here we go. Where you're storing the folder I shared with you, so we just navigate there and add on the data files folder. So I have day 2 and find there's data files. I'm going to read into R and call it test file using the read.csv command. File equals, I'll just do number 1 because I know that one has a blue column. Header equals true. Now let's try using our function. I type the name of the function as with anything else, my plotting function. Tab complete, and I can see data frame is going to be equal to my test file data frame. And the plot name, I just have to give it some name to run with. I'll just call it test in quotes. And I can run this line of code, command return. And then my graph has been made in the bottom right. I got a warning message, but warnings aren't errors, so it's still executed, and it made the graph. Oh, I know. Yeah. Okay. There's a function. Any questions on writing a function? Okay. We actually could, at this point, do some of the first breakout activity. Yeah. Cool, let's do that. All right, I had more in mind for this exercise, but we'll just come back to that tomorrow. We're gonna stop here for instructing material, and I'm going to give you a new task, as long as, right, there are no questions on the day's material or functions in general. Real quick, open for questions. Okay, cool. So here's a new task. Modify this function so it makes an XY scatter plot if the average value of that first column is less than 0. Okay, so that is the task for now. Actually, what I'll do, make this all visible. Cool, so for the remaining 10 minutes, go ahead and work with the neighbor on your own as you wish on this last exercise. And then tomorrow when we come back together, we'll go through this task as a group and then continue with the material. Cool. And then Don and I are around to field any questions you have as you work on that. Right. There's more code coming. Okay, so yeah, so you can't edit this. This is technicals here that you need to do. So go back to where you actually did.
Oh, okay.
Yeah, there might have been something. How it was first run.
Is it supposed to be data dot frame? But you put data dot frame.
Your data.
Yeah. So data frame.
Yeah. I called it test one. Inside R,
But you're calling it data, but it's dot.
Oh, yeah.
I'm not sure what you're asking.
I accept working
Did
directory.
you run a script?
I
Did you run a file or did you copy all the things that's one of the
I just run this 2 months.
Okay.
Yeah. But didn't some anything like big afterwards.
Well, usually when there's an error,
Oh, here. Oh, okay. Okay.
Overview page, yeah. This one here just means that we change the name. Yeah, we change the name of the file. Yeah, so it has all the entries that want to be but has so that so they both do the same. So if you open them up within Studio, yeah, yeah, yeah. Yeah, but you put them both in there. That's all the version. They're still different. So I'm missing kind of. Yeah, so like it comes. I didn't want to for just for like separate. So whereas here it's like overwriting. So first we remove all the names from box, we call it a new thing. And I'll also just instead of having always type box.trim, I'll just type box. So I reassign box.trim. in the end, they're the same. Yeah. So that's when you have multiple groups that you're making out of, and you want them to all start at a vertical 0. If you don't have positions with identity, then the digograms are stacked on top of each other. Kind of, instead of right, so like in the histogram, one group and then the next group is blocked on top of the next group. For that, identity just means that they're not side by side, they're front to back. Not on top, but not the side. It's literally like the first one is wrapped in on top of that in front, the next one is wrapped, and then front of that is wrapped. That's where you're really transparent. You can sort of see through the front one. Only one square bracket to go on one, not the whole. Yeah, because the square brackets in one is indexing them, and then we're comparing that index value. No, because it's here too. Yeah. Yeah. Interesting. Yeah. Try typing names in here. Just anywhere. I just mean anywhere you have like a blank line. So we can try this out. In parentheses. I'm sorry. Put talks inside of parentheses. So we're going to run a function on the talks file. Great. So now this tells us the names of the columns, but this also allows us to change the names of the columns. Yeah. So if we take this names of box and we put at the end of the square brackets 1, it will return to us the first column name for them. So go ahead and try adding square bracket 1. Square bracket, so inside of the square brackets run that line. Great. So now we have this first one that's causing the trouble. So now we can go back up here again and use the assignment operator, right? So the less than sign. That one. Perfect. And, no. Hyphen. Okay. And then in quotes, we now type whatever name we want to replace it with. We don't have to. You can put spaces in there if you want. Sure. if you wanted to work with the rest of the coding element, yeah, capital S. Great. It's just changed it. Yeah. So if you click up here to look at the file again, or you run Box, you can see the what it's been changing to. There it is. Oh yeah. So it's somewhere. So the plus sign just means that you were running a block of code and you never got to the end. Maybe it's in the middle of the loop or the then statement. Yeah, you just didn't execute the rest of it. And so the plus sign means it's just waiting. So to get out of that, you just hit escape. And then now you can start fresh. Also, yeah, we're at 5 past, so we're technically done. Feel free to exit if you like. I'm happy to stick around for a few minutes. But we're done for day 2.
Question. So,
Did anyone come in late that needs to sign the roll attendance?
There were just thanks. Right. So before we had this if condition on whether or not the name was called. Now we're going to make the condition be something like an average value.
Do you have the attendance sheet? Last time I had mine for stats. I think this is mine, right?
This one.
Is it online? Oh, for today. Okay,
Yeah, this
great.
is for today. Yeah. So you have to imagine going to calculate the mean value of the first
Okay.
column. How we can do it.
Great.
And then that becomes the code. And put it into the list. If that's the one you want. Yeah. We will.
And then also the code.
Yeah.
There we go.
I really removed all of those and then all of them. Yes. Oh. Okay. So maybe there is a yeah.
Yeah, I felt like I had.
Can you run that one? How'd you do it? Mhm. Oh, this is backwards. This should be, it should look the complete opposite. The little, no, the little arrow. Yeah. It's, the dash was after the arrow, the less than sign. Less than dash. Perfect. So you can actually get a copy of the entire chat thread with the video.
Okay.
So when I stop Zoom, stop recording.
Does it get private messages or only public?